Let's talk about right triangles today and the trigonometry of right triangles, shall we? And I have a triangle ABC in this position, and I think you will agree that we can always take a triangle and construct a triangle congruent to that one, so that we then would have an angle which would be in standard position. Would everyone agree with that? Such that angle alpha here would be congruent to the angle BAC in our given triangle as we see it here. Well, we can go ahead and make our definitions of the sine and cosine and what have you of angles of a triangle just as easily as we have with respect to our coordinate axes. And we'll rely on our coordinate axes in order to do so, okay? So that, for example, if we're interested in the sine of alpha, rather than calling it this height, let's give this the name A and C and a little b, rather than calling it simply A over C, we could also talk about the side which is opposite, or the length opposite the given angle, divided by the length of the hypotenuse. Is that right? And rather than my writing all of that out here, let's actually just use the letters to indicate that. In other words, the sine of alpha then is going to be, by definition, what? You'd like to say again that it is going to be what? A over C. And the cosine of alpha, of the angle alpha, then is going to be equal to, we may think in terms of the length of the adjacent side divided by the length of the hypotenuse, which is then going to be, using our letters, B over C. Similarly, the tangent of alpha, and in fact, let's look at our triangle, our given triangle of ABC. The tangent of angle alpha, which is then going to be this angle, is going to be what in name?
A over B.
The opposite side over this adjacent side, which is A over B. Well, the cotangent of angle alpha then is B over A. The secant of alpha is C over B, and the cosecant of angle alpha is C over A. All right? So this comes directly out of our definitions of our trigonometric functions. Let's look at A over C again, and perhaps looking at this given triangle as we see it here, A over C, in terms of angle A here, or the angle BAC, is a name for the sine of the angle. But then what may we say about A over C in relation to, say, angle B, or rather angle beta? And let's now think in terms of our triangle and concentrate on angle beta. And what then do you think you may see there? Looking at angle beta here, A over C would be a name for, Doug? The cosine, and this then is going to be equal to the cosine of beta. Let's use the Greek letter beta to indicate the angle. Similarly, the cosine, well, let's look at B over C. And B over C in relation to angle beta is going to be a name for what? This is equal to the sine of angle beta. Now, how about A over B? Looking at our given triangle here, A over B then is going to be a name for what? The cotangent. Very good. The cotangent of angle beta. And then B over A is going to be a name for what in relation to angle beta? Don?
Tangent.
That then would be the tangent of angle beta. How about C over B? C over B in relation to angle beta is a name for
Cosecant.
the cosecant, CSC of beta. And also then C over A would be a name for what? That's a name for, Tim?
Secant.
The secant. And this then is the secant of angle beta. Okay? Now, let's look at the triangle. Now, since we're dealing with the right triangle, A prime, B prime, C prime, what then do we know about angles alpha and beta? What do we call those two angles? They are going to be complementary angles. Is that right? Therefore, certainly angle beta is going to be equal to 90 minus alpha. And so another name for beta that we may substitute right here is what? 90 minus alpha. Therefore, we have the cosine of 90 degrees minus alpha. Now, let's look at that. Reading from left to right, notice it says that the sine of alpha is equal to the cosine of 90 minus alpha. And the name cofunctions is coming out for this very reason as we see it here. Two angles, alpha and beta, are, if they are complementary, then the sine and cosine, the co-function of the sine, is such that we have this relationship right here, namely that the sine of alpha is equal to the cosine of 90 minus alpha. What then can we say about the cosine of alpha? it then is going to be equal to the sine of what? Of 90 degrees minus alpha. What about the tangent of alpha? It's going to be equal to the cotangent of 90 minus alpha. The cotangent of alpha is the tangent of 90 minus alpha. The secant of alpha is the cosecant of 90 minus alpha. And finally, the cosecant of alpha is what? The secant of 90 degrees minus alpha. Okay? Very good. Well, let's now turn from this idea to a few applications of right triangle trigonometry. Perhaps this one isn't too significant, but let's look at it anyhow. The angle of depression of the base of a tree from the top of a 200-foot tall building measures 63 degrees. How many feet is the tree from the base of the building? Well, I've drawn a little picture here in which here you are at the top of the building. There's a definition of angle of depression that we must realize, and that is if you were to look out on the horizontal and then go down from that horizontal to whatever the point is, the angle thus formed is called the angle of depression. All right? So here we are. Now, I think you will agree from your work in geometry that if this angle is 63 degrees, then certainly this angle here is also going to be 63 degrees. Now, the height of the building is indicated here by this length of BC, which is 200 feet. And now we're interested in the length B. Now, looking at the angle of 63 and the number 200 and this number B, and thinking of your definitions of the trigonometric relationships, which one of those trigonometric relationships would be most useful for you? And perhaps it would be preferable to have the number B in the denominator. In the numerator. Let's think about that. And what trigonometric function do you think would give that to you? Malcolm? The cotangent. Because what can you say? The cotangent of 63 degrees is equal to B divided by 200. Is that right? B divided by 200. And therefore, B is going to be equal to 200 times the cotangent of 63 degrees, and that immediately gives you the value of B. Okay? Well, I've already looked up in the tables before the lesson started what the cotangent of 63 degrees is, and it turns out to be 0.5095. Now, let's read our numbers, taking these values of 63 degrees and 200 to be precise measurements, that is, exact measurements. And if we were to do so, the number of 63 we can read directly in our table, and it would then give us the cotangent would be significant to 4 digits, okay? So now we have here 200 times 0.5095 is what? 2 times 5 is 10, 19, 10, is that right? And therefore, our decimal point is where? What is our number that we want? But what's our number, Doug? 101.90. But since our original number here is good to 4 significant digits, our final answer then you would like to say is equal to what? 101.9. Well, let's say, I think this would be good just to 4 digits. Is that right? Okay? Everyone agree with that? If I multiply this number by 2 and then come over, and then by 200 and come over the 4 places, I think our decimal point is right here. Well, I think this illustrates an agreement that we would like to make, and that is if we have a relationship between degree measures and significant digits, let's agree that if we have an angle measured to the nearest degree, all right, to the 1 degree, then this would correspond to 2 significant digits in the length of the side. If we had, say, to the nearest 10 minutes, it then would correspond to 3 significant digits, and if it were to the nearest minute, we then can read our answer to 4 significant digits, all right? And since in this example I have taken our numbers, we just assume that these numbers were 2 precise numbers, that is 63 degrees, exactly that number and this number. Our answer is as good as what we can read in our table, namely 101.9, okay? Let's look at another example. It says, what is the height of a flagpole if the angle of elevation from a point 100 feet from the base of the flagpole is 35 degrees? Well, if you ever have the problem of measuring flagpoles, there's no need for you to climb the flagpole in order to determine how tall it is. A little trigonometry, you can figure it out without climbing the pole. In that we have now a definition of what is called the angle of elevation, all right, which is then from the horizontal up to wherever you are reading, which is in this case the top of the flagpole. We're told that this number is 100 feet. You can simply walk out from the base of the flagpole 100 feet, take your angle of elevation, and what trigonometric relationship do you think you would like to use in order to get where you want to go? And Peter? The tangent. In other words, the tangent of 35 degrees is going to be equal to what? A over 100. Therefore, A is equal to 100 times the tangent of 35 degrees. I've already looked this number up in the table before the lesson started, and it turns out to be 0.7002. And therefore, our answer that we are interested in is what, Peter? 70.02. Again, if we assume that our measures are accurate to the, in this case, we're talking about precise measurements, our answer will be as good as our answer in the tables. So let's decide that it's 70.02. Okay? Let me ask you to do some of these numerical situations for your homework, in which this will be assignment